Alright guys, this is going to cover a fair bit of stuff, alright? This is looking at the structure of the atom in terms of physics. So, first thing I want to talk about is the different types of light we get off of one of these little guys here. So, when we are heating up a filament and making it brighter and brighter and brighter, what we're actually doing is putting more electricity through that, or higher voltage through. What that higher voltage does is makes the charged particles inside that filament vibrate faster and faster and faster and faster. When they are kind of slow, they'll be a dull red, and you might be able to see that. When they're a little bit faster, they'll be dull red with a bit of orange, and then faster, yellows and blues, indigos, violets, until it glows white hot, which is why I've drawn it in white here. So as we increase the voltage, the temperature of the filament changes, therefore the colour that the light comes off changes. Now that's fine for solid objects like this, so the charged particles are trapped and bound and all that sort of stuff. It's fine for solid things to give off light in that sort of way, but what we're looking at with the emission spectra is for vapours of gases to be doing it. So when we heat up vapours of gases, what we're actually doing is exciting the electrons in that gas. So let's look at the energy level diagram. So this is what an energy level diagram is, looks like, and this one here is actually from hydrogen. I probably sort of spread it out a little bit more so my numbers and whatever else, could be spread out a little bit more. But we effectively have what's called the ground state. So the ground state is room temperature. There's not much energy, there's no voltage, none of that sort of stuff going on. So we have hydrogen here in the ground state, and the energy level for that is n equals 1. If I put some energy into this system somehow, so it could be a voltage, could be some heat, it could be a really bright, a light that has enough energy per photon to get these electrons to do some stuff, I may be able to excite them enough to get them to n equals 2, or the first excited state. So that's the ground state, this is the first excited state. Now, in order to do that, I've actually taken some energy, so this is actually minus 13.6 electron volts, this is minus 3.4 electron volts. This negative number means it's below the surface, so at n equals 1 it's going to take 13.6 electron volts worth of energy to excite that electron so much that it reaches n equals infinity. Now it's ionized. So that's related to the ionization energy for hydrogen. But what we're going to do first of all is put some heat into the system, or some light, or some electricity, some sort of potential difference into the system. What I'm going to do is raise that electron up. Now, that electron only wants to exist in these discrete energy levels. Hydrogen's got these ones, mercury's got different ones, aluminium's got its own, xenon, fluorine, any element you can think of has its own unique energy level diagram like this, which is why vapours of everything glows different colours. It's like their own DNA fingerprints, whatever you want to call it. So I'm going to put this amount of energy in. Now, to get from minus 13.6 to minus 3.4, it's actually taken 10.2 electron volts worth of energy to get that electron to move up there. Well, this means that it's orbiting a higher shell level, whatever you want to call it, but it's got more energy now. So if I left it there, it would, stay there for a moment, not, we're looking billionths of a second, if that, and then it would drop back down. And when it drops back down, what it's going to do is give off 10.2 electron volts worth of energy. Now, it doesn't really know how to do this, so it gives it off as a photon of light. So it'll scatter off a photon, 10.2 electron volts worth of energy. We won't see that because 10.2 eV is past the visible. 1.8 to 3.2, give or take, is about the visible, maybe 3.3, 3.4. 10.2 is definitely in the ultraviolet, so it's past the visible, past the violet. And that photon will come out, and that photon is unique for hydrogen. Nothing else will do that photon other than hydrogen in this sort of a way. Alright, so at room temperature, nothing is coming out because we need some ultraviolet stuff or a fair bit of heat to get hydrogen to do this thing. So if I put in a little bit more energy, so instead of 10.2 electron volts, what I'm going to do is put in 12.09. 12.09 is going to get me, if I've done the maths right in my head, all the way to there, to the second excited state. So n equals 3, second excited state. Now, when that electron transitions back down, so what I've done is put some energy in and it's going to transition back down. It can do it in a couple of different ways. It can make one big jump and it can give me a photon of, get rid of that one so we can see what's going on a little bit better. Jesus, terrible. So anyway, what we can do is get that photon, get all the energy back as a 12.09 electron volt photon, or we can get back as two different ones. We can get that guy there plus the 10.2 that we got back here. So I'll give one on 2.89 eV and 10.2 eV. Yeah, that actually does work. Cool. So now we've got two different photons. So I've excited it to the second excited state, n equals 3, and now I've got three different photons back. So we're not just doing this for one electron in hydrogen, we're doing this for lots and lots and lots of them. So if we put in 12.09 electron volts of energy, we'll excite a whole bunch of electrons in there from the ground state, n equals 1, to the second excited, n equals 3. And on their way back down, they'll give off three different types of photons. One would be 12.09. Ultraviolet. One will be 10.2 ultraviolet, just as we spoke about before, but we'll also get this one, 2.89. 2.89 is definitely in the visible part of the spectrum. So 2.89 is visible, and we'll be able to see that one. And if we keep going up and up and up, we'll end up transitioning from the 0.85 to 1.51. I just realised it's not 2.89, is it? It's 1.89. At least I think I just realised that. 1.89. 1.89 is red. So when you light hydrogen gas, quite often you'll see red. There we go. Now it's red. So every element does this. You put a specific amount of energy in, and you get a specific amount of energy back out. And if I keep exciting these electrons to higher and higher and higher states, so let's say we go up to n equals 5. You could probably see that we've got a whole heap of different photons we can get back now. We're adding more and more and more photons per, energy level that we go back up. So if we keep going up and we go to n equals, let's go n equals 6, and we start transitioning back down, we've got, all of these ones. Whoops. We've got all of these ones plus that one, plus then we've got all the transitions from this one and from this level and this level and this level all the way back down. So we put one piece of energy in and we get lots and lots and lots of different energies back out. This does a couple of things. It means that we can heat up a vapor of hydrogen or heat up a vapor of a substance and detect that there's hydrogen in there, because we'll get all of these different colours back out. So you'll actually see it on a line emission spectrum, where you'll have, it'll look like a black background, and they'll be coloured, there'll be bright bands every now and then. Alright, and the brightness or the thickness of these bands sort of shows how many photons will come back there, but it might be that, we have OEG BIV, so this is giving off some red, some yellow, a bit of bluey green, and a bit of bluey purple, and that might be unique for whatever element that is. For hydrogen, it gives off that kind of red stuff, and there's some others that are slightly bigger, but hydrogen has its own unique one, and so does every other element. Now, if I was to give the electron at the ground state 13.6 eV, I'm actually going to ionise that hydrogen, so it won't have a chance to come back down and transition back and give me all of those different things. One of the coolest things I've seen is what's called Fraunhofer lines. So the sun gives off a whole bunch of light. The sun is actually an incandescent light source. It's giving off, all of the colours of the rainbow, every single one. There's no gaps, nothing. And what happens is the sun's light comes out, and outside the sun is this vapour. So it's a huge big gas cloud around the sun between it and us on our pale blue dot. All right, and as the sun's light goes through this vapour cloud, it's light going through a vapour cloud. So if I put light energy into this hydrogen vapour, I'll get the electrons excited up, come back down, scatter off photons. So what ends up happening is this raises elements up energy levels, and then they scatter off photons. So the photons that were coming straight at us aren't necessarily going to be re-scattered straight back at us. They're going to be scattered in all different directions. So what should look like perfectly even spread of white light, we actually have bits missing, colours missing. And the colours missing in the Fraunhofer lines show us exactly what our sun is made of. And we can look at it and see the hydrogen, and we can see the line spectrum for hydrogen and helium and sodium and a whole bunch of other stuff. And it's because it absorbs it in this sort of vapor cloud on the outside, which excites its electrons up. They transition back down, give off those photons, but don't necessarily point those photons straight back at us. The emission spectra is when you heat stuff up and it, absorbs those photons. So you would have, and then gives them back off. The absorption spectrum is pure white light with black lines missing, which is what you'll see with the Fraunhofer lines. So the Fraunhofer lines are absorbing, it's an absorption spectrum, and emission spectrum is when you heat something up and it gives the light back out. The way to find out the wavelength is from calculating the difference in the energy levels. So here you saw I eventually got 1.89 electron volts. You know that E equals HF, so we can find out F is E on H, and using the 1.89 electron volts converting to joules, divided by Planck's constant, we can find out the frequency, and from that we can find out the wavelength and determine what colour it is. This wavelength is also what we can use in the spectroscope. Remember D, sine, theta and lambda, so we can actually find out the wavelength based on the angle that it diffracts through. All of these wavelengths, remember, are related to specific transitions. These wavelengths also will diffract through specific angles, so by passing light from a source through a spectroscope or a diffraction grating or similar, we can actually break up the white light or the coloured light that it gives off into all the different unique ones that it gives off, and then match that against known samples and determine what those things are made of. It's as simple as pointing a telescope at a star, running that light through a diffraction grating, and then reading off a chart exactly what that star is made up of. It allows us to work out roughly how old our star is, compare it to others. If I was to get this Roy G. Biv here and sort of shift it to the blue end, and you looked at it and you saw that these four lines were spaced this far apart and are this bright, which means that, oh, that's definitely, let's say, potassium. It isn't, so don't quote me on that. Let's say it's potassium, but it looks like it's shifted to the blue end a little bit, so everything's been kind of picked up and moved, let's go 10 nanometers across from where it should be. We could say that that's actually been blue shifted, and blue shift is a relativistic thing from Doppler effect and relativistic shifting in frequencies. So we would actually be able to say that not only is that star got potassium in it, but it's actually a star that's moving towards us. And similarly, if that was shifted the opposite way, we could say that it's been red shifted, so that the potassium, the colours are all there, the spacings of all those colours are all there, but they've been shifted a little bit towards the red end, so that might be a star that's moving away from us. So using this, running light through a spectroscope, getting this to do the diffraction thing, means that we can calculate the different colours, the different energy levels, find out what elements are in a star, and then also work out whether it's coming towards us, moving away from us, or roughly the same distance, or moving through the universe at the same speed as us. And that is actually just really, really cool. Really quickly before I finish this super duper long one, I also need to talk to you about fluorescence. Now, fluorescence is the process of putting one specific amount of energy in. So let's say in this version here, we're going from 13.6 up to minus 13.6 up to minus 0.38. So we put in 13.22 bits of energy, and so that's our energy into the system. And fluorescence is the you put in one amount of light or one amount of energy, and you get it back in all of the different colours that it will come back in. So the blue line that I drew before that goes all the way up to n equals 6 is the one piece of energy we put in, and we get that one out, get that one back out, but we also get all of the other blue ones, which I will continue to fill in now. So we get that one, and we get that guy, we get that one, plus we get that one, plus we get that guy. we get that one, plus we get that one, plus we get that one, plus we get that one, and that one. So you can see I've probably missed a couple now. You put one piece of energy in and you get that back in lots and lots and lots of different steps. So a fluorescent light globe that's above me right now, above you guys probably right now, you put in, you know, the voltage from the potential difference in the plug, I guess. That one piece of energy in raises a whole bunch of atoms to a certain energy level, and then the electrons cascade on their way back down. So it's like going to the top of a staircase and then going down one step at a time, or going down 2 steps at a time, or going down 1 step, then 7 steps, all the way to the bottom. So there's different paths for the light to, or the electron, sorry, to transition down in order to make it back to the ground state.